Good morning. This is part 2 of our kinematics video, part 2 out of 3. We already talked about displacement and significant figures. Next time we're going to talk about average velocity, average speed, and instantaneous velocity. Okay. Remember that these equations are going to be developed under the conditions of constant acceleration. Okay. And we're going to develop the equations that are going to give us the velocity and the position at any given time. We'll cover free fall later. Okay, just to review real quick, displacement is whatever your position is on your x-axis in one dimension is your final position minus your initial position. Okay, x1 is where you start at time 1, x2 is where you stop at time 2. Okay, so for x1 is 5 meters, right there at 5 meters, we stop at 12 meters, it's your x2, 12 minus 5 is 7 meters. Average velocity is just simply the displacement over the change in time, the change in position over the change in time. So we can take our one-dimensional position here, we can talk about time and position. We can start out, say, here at -5 at t equals 0, and at, let's see, what time is that? Time 3 seconds, we're at 3 meters, and at time 4 seconds, we ended up at 2 meters. Okay, and so we can graph these. This is position versus time. And if we take a look here, let's take a look at this first graph here. If the position is not changing, we just simply have a flat line. Okay, that's a constant position. If you have a constant velocity, that of course will also show up as a flat line in a graph of velocity versus time. Okay, constant acceleration, which is the condition for all of these equations, you're going to have a whole set of flat lines. Different regions may be different values of flat line, but there you are. Okay, at units of meter, average velocity and velocity are just going to be meters per second. So we can graphically determine the average velocity. We'll take 2 points here. So x2, time 2, and time 1. Okay, what is our initial position? x1 and t1. So we're going to start here at time 0. Oh, actually, let's see. This is time 1 second, whatever time 1 second is. And then position at time 1 is -4. Yeah, that's about right. About -4. All right. And then at time 2, we have 2 meters and 4 seconds. All right. So the change in position, our displacement, final minus initial. Remember, our initial was a negative value, so 2 minus a -4. Okay, that's 6 meters. So 1, 2, 3, 4, 5, 6. So from here to there is 6 meters. Okay, and then from, in this example, 1 second to 4 seconds, 4 seconds minus 1 second is 3 seconds. 6 meters divided by 3 seconds is 2 meters per second. Okay, your average acceleration, the average acceleration is just simply like the average velocity, was the change in position over time. This is the change in velocity over time. Notice this is meters per second. We're going to divide by seconds again, meters per second squared. All right, and let's go ahead and let's take a look at this. Okay, so here we have, the condition is that for all of these equations that we're going to have constant acceleration. Here we have 3 different periods of constant acceleration. We have no acceleration at all, 0 acceleration, right? And pretty much everything should be a constant at this point. Then suddenly it jumps up to 2 meters per second squared, jumps back down to 0, and it falls back down to -4 meters per second squared before jumping back to 0. Let's take a look at our velocity here. Okay, so our rate of change, our slope of the velocity graph is going to be 2 meters per second squared. Okay, so initially this is going to be 0. This acceleration is 0, so your slope is 0. That means you're going to have a flat graph. This slope is positive, which means your velocity is going to be going up. We've transitioned back to a 0 acceleration or a zero slope on our velocity graph. And again, we can see here that we get a flat graph here for velocity. And now we have a negative acceleration, which means we're going to have a negative slope on our velocity graph, and that is falling down like this. Okay. Now, what does that imply about our position? Well, here our velocity is 0. It's 0. So our position isn't changing at all. Now here, starting at about 1 second, the velocity is going up. All right, it's going up. It's a little bit more each time. So this position graph is going to be changing, but then it's going to reach some. Wow. It's going to reach some maximum value, the rate of change. In other words, the slope is going to reach some maximum value. Then during this period here, it's going to remain constant, which means our slope is constant. Our slope of position is constant. And here, our position is very positive, so it's still going up, but that slope is headed down towards 0. In other words, back toward another flat line. So what that means is that your slope here is now becoming more and more and more flat until the position graph is now constant again. All right. Okay, we have higher order rates of change. You don't always have a situation in which acceleration is a constant. You can have acceleration changing, and the rate of change of acceleration, believe it or not, is called jerk. Higher even that, the rate of change of jerk is called snap, and the higher than that is snap, crackle, and pop. All right, just be aware that they exist, okay? But we don't really deal with those, at least not in this course.